Okay, you solve for this equation. Once you do that, you should be able to get the value for the rate constant. This is how you get it. And you in that way, you would have solved, or you would have calculated or solved the question. So it's very simple for this one, because once you get the rate constant or the rate of the reaction, okay, the rate law, then it's easy for you to get the rate constant. Just make the subject of formula and then pick any one of the experiments in the table and put the values for the rate and also for the concentrations that are given in that experiment. Then once you do that, you have calculated the rate constant. Any questions on the rate constant? Any question? I am pausing a bit. Any question for the rate constant? Okay, it seems to be straightforward. Okay, so that's how you get the rate constant. So today, I want to start from here as our next subtopic, which is called the integrated rate equation or the integrated rate law. Okay, so far in terms of rate laws or rates of reaction, we know that rate is equal to change in concentration. If A is a reactant, then you put a negative. Change in concentration over change in time. This one we did, that was the first equation we did for the rate. Okay, rate in terms of the reactant is negative. Then we have also learned the rate law, that rate can also be given by K, change in concentration for the reactant, raised to some power, okay, raised to some power, okay? So we are going to call this as M. So we've looked at two types of rates. You can have two ways in which to calculate the rate of a reaction. So the integrated rate law really combines these two rates together because their O rate is equal to rate. So it combines these two equations together. So this is what, then when you integrate the equation, it gives you what is called the integrated rate equation or rate law. So let's see how this is done. Let's see how this is done. So for example, let's start by looking at the integrated rate law for a first order reaction. Let's look at the integrated rate law for a first order. So in the first order, our value for M will be equal to 1. M will be equal to 1 in this case because we are saying it's a first order reaction. Therefore, we are looking at rate is equal to this equation and rate is equal to this equation. This is coming from the rate law, okay? This is coming from the rate, okay? So we have two equations for calculating the same thing, which is the rate. You can use the integrated rate law, sorry, you can use the rate law, then you can use also just the rate of equation, change in concentration over change in time. If this is true, therefore, if this rate is equal to this rate, therefore it means that this part will be equal to this part here. So this is what I've given you in this equation here. You can see that, okay? The average rate is equal to the rate law, okay? So you have combined these two equations together, okay? We have combined these two equations together. So let me wrap this as I go to the next part. So the next thing now is if I'm going to calculate I integrate these two equations, then I should get what is called the integrated rate law for the first order reaction. I will be able to get the integrated rate law for a first order reaction. Okay, so let's see how you integrate this part. So take note that in the questions or in an exam, in a test, we might not ask you necessarily to integrate this equation, but I want you to take note of the final equation that will come out after I do the integration for you. Okay, so let's see how the integration is done. So for a small change, you know, we say we normally put a D to represent a small change. Instead of a delta, we put a D there. Okay, and then we put a D there. It's the same. For a small change, we use a D. For an average, we use a delta. We use a delta. So assuming that the rate moves a small distance, it has not gone all the way up to completion, but it has just moved a small, a small time. It has a small time has elapsed. Okay, so therefore we use D instead of a delta. We use D because D means a small change that has taken place. So therefore, using this equation, I can make dA the subject of the formula by taking dt on the other side. If I take dt on the other side, then what I remain with is this part that I've written for you here. Negative dA is equal to K concentration of A dt. This is for a first order, so the value to which A is raised is 1. Okay. If I integrate on both sides, okay, which I'm doing here at this point, then I need to get the like terms together. So here, since I'm integrating with respect to dA, okay, the concentration of A on this side has to be taken where the A is. In short, I'm saying put the like terms together. So once I put the like terms together, I have this equation here, and the negative has gone on the other side. Okay, then I integrate on both sides. I can integrate on both sides, which gives me this equation that I have here. I've integrated on both sides. So you know from integration, if I integrate 1 over x, I simply get natural log of x. Okay, so if I integrate 1 over a, I get natural log of a. Okay, this is from limit x2 to x1. So this becomes my integration. And the limit here is a1 and a2 and a1. Okay, so if I do that on this equation here, okay, if I do this on this equation, then I divide throughout by natural log. I make change in concentration of A at time t, the subject of formula. Then I end up with this equation. This is the equation that I want you to get and memorize if you can. Okay? This is the equation, the one that I've put in orange, okay, or pink if you like. This is the equation that I want you to memorize. This is the integrated rate equation for the first order reaction. I'm saying this is the integrated rate equation for the first order reaction, this one here, okay. So if I want it in the natural log form, then this equation can also be written in a natural log form as the one that has been shown here. These two equations are the same, okay? These two equations are the same. The other one expresses in terms of exponential, the other one expresses in terms of natural log, okay? Now, this equation is very important because it helps you to find out how much of the A will remain after a certain time of reaction has occurred, okay? How much of the A has remained. So A at time t is the A that will remain after t minutes or seconds have gone by. Then this A to the power A0 means the initial concentration. This means initial concentration of A, the amount of concentration of A that you started with when the reaction was starting. This is the final concentration after some time T. Okay, so this is final concentration after some time T has passed through. So imagine you have a reaction or you have a reactant, then you start the reaction and then you start the time. Then you are asked to say, after 30 minutes, how much of the A was remaining? So that is the A at final or A at time T. Then this is the A initial. Same applies to this reaction, this equation. This is what these two means, where the K is a rate constant and T is a time that you are dealing with. Okay, so I've put this explanation down here. You can see I'm saying A0 is the initial concentration of A at time 0. Then AT is the concentration of A at some time T during the reaction. So this is why, or this is how the integrated rate law is used. It is used for calculating the amount of time that is needed for a particular reactant to decrease to a certain amount, or you can calculate how much A will remain after a certain amount of time. Okay, so these two are used. You can use any of these two. They mean the same thing, the integrated rate law for a first order reaction. You can use any of these two. Any questions so far? Okay, so I'll give you an example so that you see how it is used. Okay, so this is the integrated rate law for a first order reaction. Now this equation, when you get this equation, it looks like an equation of a straight line. Okay, this equation, it is an equation of a straight line in the sense that I can expand this equation. I can expand it. You know that division in logarithm is the same as subtraction. So I've just written it here differently, where I've expressed this in terms of subtraction, because in logarithm, division means subtraction. So I have this equation here. It's the same one with this one. Okay, I'm just expressing it nicely, or nice the way I want it to be. Then if I take this on the other side of the equation, then I end up with this equation down here. Okay, this equation is the same. I've just manipulated the logs there. These equations are the same. Now this equation is the same as an equation of a straight line, where this C is represented by this term here. You can see that this whole term, natural log of the concentration of A initial, is representing the C, whereas the M here, which is a gradient, is represented by the negative K. And the X here is what is the T there. And the Y here is what is the whole load of this thing here. That is the Y. So this is an equation of a straight line. So what that means is that if I plot a graph, just a minute, let me go back. If I plot a graph, since this is an equation of a straight line, okay? If I plot a graph, let me just change the color there. If I plot a graph from here, where I know my Y, so if I plot a graph of Y, if I plot a graph of Y, which I know that my Y now is natural log of A, this is my Y, at time T, against my X value here is time. If I plot a graph of this, I should get a straight line with a negative slope, because my K is negative here. So I should get a straight line with a negative slope, where the gradient of this line, the slope of this line, is equal to negative K. So if I plot a graph and I get the slope of this line, which is change in y over change in x, I should get the value for the k value or the rate constant. So this is one way you can get the rate constant by plotting a graph of natural log of time, concentration at time t against t. I get this. Now take note here. It is only for a first order that when I plot this against this, I'm going to get a straight line. You'll see then later on that for a second order, it's not this that you plot for you to get a straight line, because we are also going to look at the integrated rate law for a second order. This plot of natural log of A at time t against time, giving you a straight line, only applies to a first order reaction. Take note of that. This only applies to a first order reaction. And this is also one of the ways you can tell that the reaction is first order, by plotting this against this, and then you get a straight line, then you know that the reaction was a first order reaction. Okay, so let me just rub off this, then you can move to the next part. Okay, so this is what this slide says here, what I've just explained there. We are saying if a reaction is first order, a plot of natural log at time t versus t will yield a straight line with a negative slope. And the y-intercept is basically this guy here. The y-intercept will be natural log of A at t, A initial. So I've already explained this. So we are saying this can be used, this type of graph can be used to determine the order of reaction. So I've said, and I'm repeating, for a first order, if the reaction is first order, a plot of this guy and this guy gives you a straight line with a negative slope. And this only applies for a first order for this plot that you are doing here. It's only the first order that will give you a straight line. Okay, so I've already explained this part here. Let me move to the next part here. Here is an example. Okay, here's an example of how a question can be given for that particular that particular integrated rate law. It says, consider the process in which methyl isonitrile is converted to acetonitrile. So this is the reaction. You can see the reaction there. Okay, the question is, how do we know, okay, this is a first order reaction? So in giving you this, they'll also give you the data like this one. They might give you the data in form of a table, okay? They might give you this data in form of a table where this time around, instead of using concentration, they are using pressure. So they'll give you this data in form of a table, so you can have time, okay? You can have time there. Okay, they can give you time against pressure instead of concentration. Okay, I'm having a class. Okay, so now you can have data like this. Then they extract this information that is in here. They extract this at time is equal to 0, for example. They will give you that the pressure was 0 as well. Okay, at time is equal to 1,000, 10,000. You can see from the graph there. Then this pressure, no, at time is equal to 0, it was about 150, not 0. Somewhere here, 150, somewhere here. Then this should be 140. 140 here. Then at 20, so they can give you a table like this one. Then they ask you to say, determine whether this reaction is first order or not. At 2,000, maybe you have about 50. 20,000, you have 50. So they'll give you a table like this. Okay, or this can be concentration. It depends with what they give you. It can be concentration depending on what they give you. Then they ask you to say, is this reaction first order kinetics, second order, or zero order? So because they've given you this data, remember that for a first order reaction, from what we've looked at, a plot of concentration versus time, gives you a curve. We saw that curve last time. Okay, for a first order it gave a curve, and for a second order it gave a curve. So this will not be helpful because they've given us because the two for a second order and for a first order, all of them give you a curve. So you will not know whether this is a first order or this is a second order. The other graph that we looked at earlier was a graph of rate versus concentration. And we said for a zero order, it was a straight line. Okay, you remember for a first order, it was a straight line like this. For a second order, it was a curve like this. You remember this? This is for a zero, this is for a first order, this is for a second order. So this information given here is not helpful. You can't come up with this. You can't come up because you need the rate. What you've been given is pressure. You have not been given the rate. So you cannot use this. You cannot use this. The only one you can use is the graph for the integrated rate law, where you are plotting, you are testing it. You want to check the natural log of A, the natural log of concentration against time. And if it's a first order, we are saying it's going to be a straight line. This is what you want to test. So what do you do now? Okay, what you do now is that you extract this information. You can see that a plot of pressure against concentration gives you a curve. This could be a second order or it could be a first order. Okay, it can be a first order or it can be a second order. So here you cannot use this. It's not possible for you to use this here that we are using, because this has been plotted for us. It's the one that has been plotted here. So it might be first order because it's a curve. It might be first order. It might be second order. So we are going to try it using the integrated rate equation. Okay. So let's do that now. Let's see. Let me just grab off whatever is inside here. Okay, so what was done here now, if you want to know whether it's a first order reaction, remember that I've given you two equations in form of the E exponential, okay, in form of the exponential and in form of this guy here, okay, in form of the exponential and in form of this guy. So now what was done here is that you are going to extend this table. You extend this table here, because for a first order, what you need is the natural log of concentration. In this case, since it's not concentration, you need natural log of pressure. Okay? So since you've been given pressure, you need natural log of pressure. So now you are going to convert all these pressures in here to natural log of pressure. So you are going to get this value. So you are going to get what is the natural log of 150, what is the natural log of 140, then you put them there, all of them, you put everything there, you convert them to natural log, all of them, okay? Then once you do that, then you make a plot now of natural log versus time. You make a plot of natural log of pressure versus time, which is what was done in here for you, natural log versus time. Now, remember what we said, if it's a first order, then you are supposed to get a straight line. You can see that this is a straight line, nicely straight, okay? So this proves to you that the reaction is first order. And this is how you can know that the reaction is first order. Okay, and when you calculate the gradient of this line, which is change in y, so you can get this whole root of y value, divided by this whole lot here. Okay, you get this divided by that. So when you do that, then you are going to calculate the negative of k. Remember what we said, when you calculate the gradient of this line, then it will be equal to the negative of k. So for this particular one, the negative of k was found to be 1.5 times 10 to the power minus 5, or the slope of that line was found to be 5.1 times 10 to the power minus 5. Okay, any questions so far? Yes, Samsung.
I can ask?
Yes, go ahead.
Oh, okay. So like this graph, if we had to this one for the curve,
Yes.
suppose, yeah, like what is this curve for? So wait, this curve will help us, like it just helps us sketch this slope one we have for the first order. Like without the curve one, we can't sketch this one for the straight line.
This curve here?
Yes.
This one is not helpful.
Oh,
this
okay.
one you cannot use it. This is why I went for this one here. It's not helpful. You can't also determine whether it's first order using this one. You can't do that. You can't find whether it's first, because you see even for a second order, it will be exponential as well, and it's going to give you a curve also. So you cannot use this one. But you use the one that has got a natural log. It's the only one that will come out to be a straight line. Are we okay now?
Yes, sir. Thank you.
Okay. Anyone with a question? I'm very slow now because you asked me to be slow. I'm very slow, and I'm allowing you to ask questions between sessions. Or any questions? Okay. If there are no questions, then this is how you get the integrated rate. So you need to remember this equation for the first order. How the integrated row comes to be for a first order. Okay, so it is data like this one that will help you to know how do you come up with the integrated rate law. So depending on what you are given, you can determine the order of reaction. So this is for a first order reaction or kinetics. Okay. So here is another question over the same. Okay. Just to finish up, we have 5 minutes before we close. So you have at 1000 degrees Celsius, okay, cyclobutane decomposes in a first order reaction. So take note of some keywords there. They've told us that it's a what? It's a first order reaction. You take note of that. So you know that, oh, for a first order, I know what I'm supposed to do. I know which equations I'm supposed to pick. Number two is that they've given us the rate constant. This is the rate constant. Okay? So as you can see, the units are the ones for first order are matching with the units for a first order. So you already know that it's a first order. So number one, question one says that the initial concentration of the cyclobutane is this value here. You've been given the initial. So what have you been given? You've been given concentration of A, 0. You've been given the initial concentration for A, 0. That has been given. Then the rate constant K has also been given, which is equal to 87, sorry, which is equal to 87 per second. It has been given. Then you've also been given to say, what is the concentration after 0.01 seconds? So time has been given also. So because this is a first order reaction, and they're asking you to calculate the concentration at time t. The concentration at time t. So you already know which equation to pick. So you are going to pick the equation for a first order, which says natural log of A at time t is equal to minus kt, okay, plus the natural log of A0. So A0 has been given, you know the A0, okay? AT is what you want to calculate, okay? This is what you want to calculate. You don't know this value, okay? The time has been given, the time, you know the time. Then the K, you know the K value. K has been given to you, K. So the only thing that you don't know is AT, okay? The only thing that you don't know is AT, okay? So now at this level, this is when this equation becomes more important. Remember this equation that we said? This equation here. This is the time when this equation becomes very important. Let me change the color so that I show you the equation. This is a time when this equation becomes very important now. Because in here, this guy, you don't know. This guy has been given A0. Then K has been given, you can put it there. And then the time has been given, you can put it there. So all you need is just to put in this value, put in this value, put in this value, and solve for this one. That's all. That's all you need to do here. Okay? So this has been done for you. It has been done for you here at this point in time. So I have 1 minute before it closes. So you can just finish up this as we are closing. So here I used also this equation. Okay, I use this equation where I'm calculating this, but this has to be manipulated again. So when you do that, you can put in the values for this guy, you put in the values for this guy, you put in the value for this guy, and solve for the natural, this guy here. So when you do that, okay, when you do that, you should get the answer. So let me just quickly go to where I solved the answer there. So this is what you have now as we are closing. This is what you have here. So you can go through this. You can go through this and finish up even for part B here. So this is how a question would come on the integrated rate law for a first order. Any question as this is closing, it is closing now. 40 minutes has elapsed.